Ladies and gentlemen, welcome back to Four Wheels. Before we jump into today's deep dive, we need to talk about something that has been quietly shaping the entire automotive industry for the past few years: a narrative. For roughly the last 5 years, drivers have been told that buying a car means choosing between only two options. Option 1, stick with a traditional combustion engine and be labeled outdated, someone contributing to environmental destruction every time you press the accelerator. Option 2, switch to a fully electric vehicle and begin living with a new form of stress, constantly worrying about charging stations, long trips, and how cold weather might affect your battery. Those were presented as the only two choices. But on March 13, 2026, a company from China is preparing to challenge that entire idea. The vehicle we're talking about today is the Geely Galaxy M7. At first glance, you might think it's just another crossover entering an already crowded market. From the outside, it does resemble other vehicles from the same family, such as the Geely Galaxy L7 or even the sleek Geely Galaxy E8. But the real story isn't in the design. The real story is hidden beneath the bodywork. Because this SUV is powered by something called the Nord-Thor EMI hybrid system. And according to its creators, this system isn't simply another step forward in hybrid technology. It may completely redefine what a petrol-powered vehicle can be. Why such dramatic language? Because of a single number: 1,730 kilometers. That's the claimed combined driving range. To put that into perspective, imagine driving from London to Edinburgh, turning around, heading back to London, and still having enough range left to continue halfway toward Paris. All of that without needing to stop for fuel or electricity. Even more impressive is the efficiency. Under normal conditions, the vehicle consumes just 2.67 liters per 100 kilometers. And here's the part that truly surprises engineers. Even when the battery is fully depleted, consumption only rises to 3.35 liters per 100 kilometers. That's unusual. Most hybrid vehicles become significantly less efficient once their batteries run out. The Galaxy M7, however, remains extremely efficient even in that scenario. Today, we're going to break this vehicle down piece by piece. We'll examine the thermodynamics of the engine, the chemistry of its battery system, and the electronic architecture that makes everything work together. Because the Galaxy M7 isn't just competing with SUVs like the Toyota RAV4 or the BYD Song Plus. In many ways, it makes them feel like older technology. To understand why this vehicle is so interesting, we need to revisit a basic concept from physics: thermodynamics. Historically, internal combustion engines are not very efficient machines. In fact, they are essentially heaters that happen to produce motion as a side effect. For decades, the automotive industry struggled to push thermal efficiency beyond the mid-30% range. At that point, mechanical drive becomes more efficient than converting energy back and forth between electrical systems. By eliminating the multi-gear transmission, engineers also removed hundreds of mechanical components. Fewer moving parts mean lower weight and fewer potential failure points. Instead of shifting gears, the vehicle simply glides forward on electric torque while the engine quietly generates energy in the background. But performance and efficiency are only part of the equation. Safety, particularly battery safety, remains a major concern for many drivers. To address that, the Galaxy M7 introduces a new battery design called the Aegis Short Blade System. Most long-range electric vehicles rely on NCM batteries containing nickel, cobalt, and manganese. These batteries are very energy-dense but can be sensitive to damage or overheating. The Galaxy M7 instead uses LFP chemistry, lithium iron phosphate. LFP batteries are naturally more stable and resistant to fire. To improve their performance, engineers redesigned the physical shape of the cells. Shorter blade-style cells, combined with carbon nanotube materials, reduce internal resistance. Lower resistance means less heat during charging and discharging. As a result, the battery can charge faster and operate more efficiently. The safety testing is also extreme. Engineers performed puncture tests using multiple steel spikes driven through fully charged cells. Where some batteries might ignite, this system remained stable with minimal temperature increase. Additional tests included submersion in seawater and impact simulations. Even under severe stress, the battery chemistry remained stable. The pack is also integrated directly into the vehicle structure using cell-to-body technology. Instead of acting like luggage placed inside the chassis, the battery becomes part of the car's structural frame. This improves rigidity and enhances handling stability. Drivers benefit from better cornering control while maintaining high levels of safety. The system also supports fast charging and provides an electric